Section 9.2, the central limit theorem for sample means. So just like we were able to use the central limit theorem in chapters 7 and 8 to help us know when it's appropriate to use the normal model to calculate probabilities, we can do the same thing with means. So we can estimate the population mean as long as we can verify the following conditions. Then we know that the CLT is met and we're allowed to use that normal model. Again, remember, if these conditions are not met, then technically we cannot jump to that normal model and have it help us out. Nothing stops you from doing it, but you just cannot rely on the results. So we really do need to make sure we've got all the boxes ticked before we moved on. Okay, so once we know we can apply the normal model, what does it look like? That's what the CLT also tells us. It tells us that we would want to go into our normal model and we would want to use mu as the mean, and we would want to use that standard error formula to fill in the standard deviation, and then we could calculate results. Now, what are the conditions for sample means? We already know our conditions for proportions. How do these change when we're dealing with means? So the first condition is that we need a random sample with independence. That's the same. Each observation has to be collected randomly and they should be independent of each other. Usually for that one, we just look for that phrase random sample and we say, all right, that covers it. If it's a truly random sample, then the observations will be independent from each other. So we look for that key phrasing. Condition 2, a large sample. Well, that's the same, but how we check it is different. What we look for in the means is that either the original population is already normal. So sometimes the original population starts out normal, well then we can assume that the sample is also normal. Or we have to make sure the sample size is at least 25. So it has to be large, and what's large for us? It has to be at least 25. So we check that the sample that we take, is it at least 25. So this is a much easier check than with the proportions. With the proportions, we had to check is in p greater than or equal to 10, is in 1 minus p greater than or equal to 10. In this one, we simply look at, was it bigger than 25? So much easier check. Condition 3, we have to also have that big population. So it says if your sample's collected without replacement, which most of them are because usually you're asking people and you don't ask the same people twice, then the population must be at least 10 times larger than the sample. So that same condition would be checked here as well, that the whole population is at least 10 times the sample. Most of the time in this unit, what you will notice is that the first and the third conditions are assumed to be met, and we usually have to check that second one, which again is a lot easier to check because we're just looking for that in the problem. Okay, let's do an example. It says your whole population is all the finishing times of all men who ran some specific 10-mile race. The distribution is normal with mean 91 and standard deviation 16. So this is really interesting. The population itself is already normally distributed. So you can see how that plays into my CLT conditions above. First question is, what is the probability that the finishing time of of one randomly selected runner is within 10 minutes of the population mean? Okay, so the question first becomes, what we have to check is we're supposed to be checking, was that a large enough sample? The sample here was 1. They took one random man and looked at his finishing time, and we want to calculate up a probability. So is 1 greater than or equal to 25? No, it's not. But do we need that here? Well, it says in our condition 2, either the population has to be normal or the sample size has to qualify here. So there's 2 ways to hit this. We don't need the sample size to be large enough here because the original population happened to already be normal. So that's how we check off that condition in this case. So we have satisfied condition 2 by the whole population already being normal, which means of course, we can use the normal calculator here, and we're going to use it with what we've already got. So we're going to use the normal calculator with mean 91 and standard deviation 16. And what are we going to find? We're going to find the probability. We wanted to know the probability that the finishing time of some runner is within 10 minutes of the population mean. So within 10 minutes means up or down from this 91 average. So it looks like I'm trying to see their finishing time had to be at least 81 minutes up to 101 minutes. These are in minutes, by the way. It didn't specify that. So that's what we're finding. I'm going to go ahead and just go to StatCrunch and have it tell me this. So I'm going to go into my my normal calculator, normal. I'm going to type in the appropriate mean. Mean was 91, standard deviation was 16, and I want the between option. I want to know what's the probability of this time coming out between 81 and 101. Compute. So it gives me a nice little picture there with the between of those two values shaded, and it looks like the probability for that is about 46.8%. So there's about a 46.8% probability that any one person that you randomly choose would be within 10 minutes of that average finishing time. Okay, let's do another one. Same setup, but what's the probability that a sample mean finishing time of 9 runners is within 10 minutes of the population mean? So what if we picked out 9 random runners from this race, calculated up their average finishing time, and we want to know what's the likelihood that that average is within 10 minutes. So again here, we still don't hit the sample size. It's still not technically big enough, but we do not need it here. So we still hit that condition. But we have to be very careful here. Whenever we go to use our normal calculator, the mean is going to be the same, but the standard error is going to change. Anytime you take a sample size more than 1, your standard error changes, because remember, we've got a standard error formula, which is the whole standard error over the square root of n. So the whole standard deviation is 16 over here, the square root of 9. So 16 over 3 equals approximately 5.33. That's what we're going to put here. So just like we always had to calculate those in chapter 7 and 8, we have to still calculate that value now using our new formula. So we're going to use this normal calculator. We took a bigger sample than 1, so our standard, notice how it got smaller. Just like we expect, smaller standard error here. But we're still calculating the same thing. We're still going to find the probability of landing between these two values. So let's switch over and let's do that. All I really need to do is I need to go back in and change my standard deviation to that 5.33 value now. That's it. Recompute. So my probability here is a 93.9%. So it says, comparing the two probabilities, what does this tell us about the benefits of a large sample size for estimating the population mean? This should not really be surprising, right? Larger samples, like we got in Part B, give us more accurate results. Why is that? Because large samples have smaller standard errors. So because we had this smaller standard error here, it was much more likely that these average finishing times of these bigger samples were going to end up within that same range than any one given person, right? If you only pick one given person, you could very easily pick one very fast person or one very slow person. But once you pick like a good size sample and you average those all out, that should be closer to what the true average is. So even though this first example used the fact that the whole population distribution was normal, right? That's what allowed us to do all of those calculations. The beauty of the CLT is that as long as those three conditions are met, the shape of the population doesn't actually matter. What we know is that the more observations we take in the sample, the better approximation the normal distribution should provide. And for nearly all examples in our text, a sample of at least 25 is large enough. Although this is just a rule of thumb, if you go to a different text or if you search and watch YouTube videos online, you may see different cutoff numbers. That varies from text to text. But our textbook and for any of our MLP problems, you would be checking if that original one wasn't normal. As long as you hit that 25 mark, you're still good to proceed with your normal calculator.